Hello everybody. In this video, we're going to learn about velocity vectors and tangent lines. In the previous video, we learned about what vector functions are and how to calculate their derivatives. In this video, we're going to talk about a couple of different interpretations of those derivatives. You can think of them in terms of physics, position, velocity, and acceleration, or we can think about them geometrically, as in tangent lines. So let's begin. So first, let's say that we have a vector function p from r to rn. Our pictures will always be two-dimensional, but this does apply to three-dimensional functions as well. Let's assume that the vector function p of t represents the position of a point at time t. Now, because a derivative measures a change in a coordinate, if these coordinates represent position, change in position is also called velocity. So the derivative of a function that represents position can be interpreted as a velocity function. So I'll write that as the vector function v of t. Furthermore, change in velocity is also known as acceleration. So if you do the derivative of the velocity vector function, in other words, the second derivative of the position vector function, you have the acceleration vector function. So as an example, let's start off with the vector function for the trefoil knot. Right, it traces out this kind of pretzel shape. And so the function for that is t cubed minus 3t, t to the fourth minus 4t squared. If I evaluate this function at a point, say p of 1, we'll get negative 2 comma negative 3. So what you can think of that as is imagine drawing a vector, right, with its tail at the origin, right, in the direction negative 2, negative 3, that points to a position on the curve. And so p of 1 is a vector pointing to a point, which indicates a position on our curve. Now, the vector function, v of t, the derivative of the position function, that'll be 3t squared minus 3, comma, 4t cubed minus 8t. And that's going to be the velocity function. If you plug in any point, it tells you the direction that the coordinates are changing in. And so as you're coming along the curve in this direction, as you come towards this point, at that particular time, t equals 1, if we plug 1 into the velocity function, we get 0, negative 4. Meaning at this particular point, at the velocity, there's no change in the x direction, but the y direction is changing at a rate of negative 4 units per second. And so it's going down. Finally, the acceleration, which is the derivative of velocity, in this case is 6t, comma, 12t squared minus 8. And let's again plug in the value t equals 1. And so the acceleration at time 1 is 6, comma, 4. And if you draw that vector, it seems to be pointing to the right and up. And this is certainly not to scale at all. Right? The acceleration vector should probably be a lot longer than this. So what does it mean to say we're accelerating in this direction? Remember, acceleration is change in velocity. Right? So it's like a force is going to be pulling this point to the right and backwards. Right? And sure enough, right, we don't continue going straight down in this direction. The curve starts to veer to the right. It's also going to move more slowly because acceleration is pulling it up. And so it's going to kind of accelerate towards this direction. All right, and that's kind of a physics interpretation of derivatives of vector functions. Now, there's a little bit more information we can actually get out of this as well. So with the same position function and the same velocity function, remember that vectors really encapsulate two pieces of information. Every vector has a magnitude, which we also call its length, and it indicates a direction. The speed of this moving point along this curve, the speed is the absolute value or the magnitude of the velocity vector. And so if we calculate the length of this vector, that'll tell us how fast the point is moving at that instant. So for example, v of 1, right, that was this vector, velocity vector 0, -4. The length of this vector is its speed at time 1. And the length of this vector is 4. So it's moving 4 units per second, or whatever your time movement is, your time units. Similarly, as the point moves along, we could calculate the velocity and speed at a different point in time. Let's say when time equals 2, which point will actually be right here on the curve. We can see that v of 2, plugging 2 into this velocity function, it gives you the vector 916. And then the speed at time 2 is the length of this vector, which is the square root of 337. Also happens to be my favorite number. That's a cool coincidence. And that's approximately 18.4. And so by the time you get to this point, or this position, the traveling point is moving a lot faster, more than 4 times as fast when it gets to up here. You can even write down a general speed function, right, by saying what's the length of the velocity function. This will almost always involve a square root that can't be simplified away. This is the square root of the first component squared plus the second component squared. And there should be a 2 right here. I'm not sure what happened to that 2. Right, the length of a vector, but for x and y components, you plug in the x and y functions from velocity. So you can calculate a speed function. As another example, let's say we have the function c of t. So we discussed in the previous video, that's the function corresponding to the unit circle, cosine t, comma sine t. If we calculate the velocity function, c prime of t, that's negative sine t cosine t. Let's say we also want to calculate the speed function. Right? So the magnitude of the velocity function is the square root of the first function squared plus the second function squared. But in this case, you'll get the negative cancels out because of the squaring. You'll get sine squared t plus cosine squared t, which is actually equal to 1. You have the square root of 1, which is 1. What does this tell us? Well, it says that if there's a point traveling along this path, traveling along the unit circle, according to this function c of t, that function actually has a constant speed. And the constant speed will be 1 unit per second. And yeah, it's kind of an interesting fact. Now let's move on to some geometric ways of interpreting derivatives. And you might recall using derivatives to come up with the equation of a tangent line to a curve. And so here's an example problem from Calculus 1. Let's say you have the function f of x equals x squared. So we have a parabola. And then when x equals 3, that corresponds to the point 3, 9 on this parabola. Let's say you want the equation of the tangent line. The tangent line has the same slope at this point as the curve does, and sometimes it's described as touching the curve in only one point. Well, to calculate the equation of a line, you need its slope, but the slope is really just the change in height. The slope is the derivative of this function. Right? So the derivative of x squared is 2x, and so we need to evaluate the derivative when x equals 3. So f prime of 3, that's 2 times 3, which is 6. So we know the slope of the tangent line is going to be 6. In general, the tangent line can be written as y equals mx plus b. We know the slope, m, is equal to 6. We still need to figure out the value of b. To do this, we know the line contains the point xy is equal to 3, 9. So we can plug 3 in for x, plug in 9 for y, plug in 6 for m, and then solve for b. We find that b is equal to -9. Therefore, the equation of this line is y equals 6 times x minus 9. That's how you calculate the tangent line to a graph. And tangent lines themselves are really useful. They give you a good approximation to nearby points on the curve. But let's talk about tangent lines in multivariable mathematics. You might recall that when we first started talking about the equation of a line using this parametric vector form, the equation of a line in terms of a parameter t, we'd write that as L of t, and here I've adopted the vector notation to indicate that this is a vector producing function. The equation of a line is a slope vector times t plus a point on the line. And this can really be any point. One of the advantages to writing equations in this form is we're not limited by the y-intercept, as you would be in y equals mx plus b. But how would we go about creating the equation of a tangent line to a vector function, f of t, at some particular time when t equals c? Well, we need to calculate the slope vector and a point on the line. To calculate the point, we can say that's going to be f of c. To calculate the slope vector, well, slope is still a change in coordinates. Slope is still calculated by derivatives, no matter how many dimensions you're working in. So the slope vector is f prime of c. Once you have these two values, you can plug them into the equation of the line, L of t, and you'll be done. So, as an example, let's take my favorite parametric function, the trefoil knot function, t cubed minus 3t, t to the fourth minus 4t squared. Let's say you want to find the equation of the tangent line when t equals 1/2. Well, first, let's find a point on the line. So the point P is equal to k of 1/2. So you would plug 1/2 in for t, each of these functions, and then calculate. And this gives you this point, -11 over 8, comma, -15 over 16. Then to calculate the slope vector, we need to calculate the derivative of the function k and then plug in 1/2. So first, we'll calculate the derivative. We've seen this a few times before. Then we'll evaluate that at t equals 1/2. I'm using a bit of notation here. This line indicates evaluate whatever this expression is at the value t equals 1/2. And when you plug that in, you'll get this for a slope. -9/4, -7/2. And then you've got your slope, you've got your point, and you just put those in, and that gives you the equation of the tangent line to this curve at t equals 1/2. And you can even take the calculus 1 problem, and you can think of that in terms of multivariable math if you want. Now let's say you wanted to find the equation of the tangent line to f of x equals x squared at x equals 3, as we did before. Let's see that we get the same answer. We would first rewrite this function as a vector function. Think of the independent variable x as being represented by the parameter t, in which case y, which is x squared, is now equal to t squared. And so this graph can be represented by the vector function f of t is equal to t comma t squared. To find the point for our line, our point P is equal to f of 3, which is the vector 3, 9. The slope vector m is equal to f prime of 3. The derivative of this function, t comma t squared, derivative of t is 1, derivative of t squared is 2t. And so the derivative function, let's evaluate it at t equals 3. Plug that in, we'll get 1 comma 6. And so the equation of the tangent line, L of t, is the vector 1, 6 times t plus the point 3, 9. One final concept that's interesting to talk about geometrically involves tangent vectors and normal vectors, right? Or vectors which are perpendicular to a curve. Now, we already know how to calculate tangent vectors, right? A tangent vector is the same thing as a velocity vector. But how would you calculate a normal vector? In 2 dimensions, this is not too hard. So if you have a tangent vector, a comma b, we know the slope of this vector, slope of the tangent vector, is b over a. A perpendicular vector, or perpendicular line, should have negative reciprocal slope of this value. So b over a becomes negative a over b. And then a vector with this slope would be, for example, b comma negative a. Right, so this would be a perpendicular vector to this curve. Now, how would you find perpendicular vectors in 3-dimensional space? In 3D, we used the cross product to find perpendicular vectors, but that was a slightly different problem. Right? In that case, we were given 2 vectors, v and w, and the cross product of v and w is a new vector n, which is perpendicular to both of these. But that doesn't really help us here. Right? We're not looking for something which is perpendicular to 2 given vectors. We want something which is perpendicular to a curve. So what can we do? Now, this does turn out to be a related note, so I apologize if I seem like I'm digressing, but it's all going to come together in a glorious way. So let's assume we have a vector function, f of t, and let's think about it as representing a position along a curve. V of t, which is p prime of t, we think of that as the velocity vector that also gives you a tangent vector. And s of t, the magnitude of the velocity, that gives you the speed. Let's define a new vector function, and this is traditionally written as capital T. This can be a bit confusing because the parameter is typically written using a lowercase t, but hopefully this discussion will be clear. The function t, the vector function t, define that to be the derivative, the velocity function, divided by the magnitude of the derivative. In other words, the velocity function divided by the speed function. Right, so what we're really doing here is we're taking the velocity function, and the length is just a number, and so it's like we're rescaling the velocity function. In particular, you might remember we've done this for ordinary vectors before, numeric vectors, and this produces a vector of length 1, which is called a unit vector. Since we're doing this operation, dividing by the length of a tangent vector, we'll call this the unit tangent vector. Right? So a unit tangent vector has length 1. Right? The length of this vector is 1. Now, also, on a related note, hopefully you remember that the length of a vector could also be written using a dot product. So the square root of the vector dot with itself. In that case, we know that's equal to 1. And from this equation, go ahead and square both sides. That gets rid of the square root on the left, and on the right, 1 squared is still 1. So we know that for this new function we've defined, the unit tangent vector, capital T dot with capital T is equal to 1. Now let's bring in the calculus. Let's go ahead and differentiate both sides. The right-hand side is easy because it's the derivative of a constant. The derivative of any constant is equal to 0. To do the derivative on the left-hand side, we need to recall the dot product rule for derivatives, which conveniently looks like the regular product rule. The derivative of the first dot the second plus the first function dot with the derivative of the second. Now, these two dot products are actually the same thing, right? T prime dot t is equal to t dot t prime. So we really have the same quantity twice. So 2 times that quantity equals 0. And we can simplify this equation by dividing both sides by 2. which gets rid of the 2 from the left-hand side. And we're left with t dot t prime is equal to 0. So a long time ago, we also learned that when the dot product of two vectors is 0, those two vectors are perpendicular. Right? So the vectors capital T and capital T prime are perpendicular. So we just we let the vector function n equal the vector function t prime. In other words, derivatives of unit vectors produce perpendicular vectors, which is, at least in my mind, kind of surprising and neat. Right, but let's do an exercise here. We've learned a lot about a lot of different interpretations, both physics related and geometry related. So let's test that. You learn math by doing math, and let's try an exercise involving this function. F of t is equal to t squared minus 1, comma 3t minus 1. I'd like you to calculate these different things. So the value of this function at 2, the velocity corresponding to this position at 2, that means you'll have to calculate a derivative, the speed at 2, and so that would be the length of the velocity, the acceleration at 2, so first you need the second derivative of this position function, and then plug in 2. Then the unit tangent vector at 2, which you can get from some of the previous parts here. And finally, the equation of the tangent line, in parametric vector form, of course, the equation of the tangent line at t equals 2. And again, you're going to be able to get that using some of your previously calculated information. All right, and this is a good stopping point, I think, for this topic. Thanks for watching.